Hello everyone, I'm Murali Brahmadesam, Director of Engineering, Aurora Databases and Storage. I would be introducing Amazon Aurora Serverless V2 for instant scaling for demanding workloads. And I have Chayan Biswas here to do a demo as well. Let's dive in. What's Amazon Aurora? Aurora is a managed database service with performance and availability of high-end commercial databases with simplicity and cost effectiveness of open source databases. We have drop-in compatibility with MySQL and PostgreSQL. That means that you don't have to rewrite your application if you already use these databases. And we have a simple pay-as-you-go pricing. Let's look at the architecture. Aurora uses a cloud-native database architecture, and we focused on compute and storage separation. If you look at the diagram, the top half represents the compute and the bottom half represents the distributed storage. Let's look at what goes into the compute. The compute comprises of SQL query processing layer, the transaction layer, and the caching layer. The SQL query processing transaction layer uses a lot of CPU, and the caching uses the memory. Our core idea is log is the database. We implemented a purpose-built distributed storage system for databases. The distributed system understands log records and pages. The storage volume is striped across hundreds of storage nodes distributed over 3 availability zones. We store 6 copies of data with 2 copies in each availability zone. The database engine itself uses 4 out of 6 quorum that provides write availability even with 1 easy failure. With this architecture, what we were able to do is to offload some of the compute requirements from the traditional database architecture into distributed storage. For example, in the traditional architecture, the database engine would have periodically done checkpoints, and it writes the log records for recovery. In case of Aurora architecture, we eliminated the need for checkpoints. We use log as our database. That means that the database engine sends only the log records. And the distributed system periodically does checkpoints so that the database engine CPU is not needed for that activity. The same way, we do backup restore on the distributed storage, and that also relieves CPU and I/O requirements from the database engine. So essentially, by separating compute and storage, we eliminated the database instance, the compute instance, from a lot of compute and I/O work and pushed it to hundreds of storage nodes that backs a particular database. Let's look at how we achieve compute scalability. The distributed storage that we have built has ability to attach multiple database compute instances to the same storage volume. In this diagram, you can see that you have a single writer attached to the database volume, and you have multiple readers. We can attach up to 15 readers across multiple availability zones to the same storage volume. If the writer fails for whatever reason, due to hardware failure or for whatever reason, it can fail over quickly to a reader and promote it to be a writer. The writer, when it generates the log records based on the change that needs to be durably persisted, it sends to the distributed storage, and it also immediately sends to the reader so that the reader can serve the latest data. And because it's just a network hop away, typically the readers are less than 10 milliseconds in terms of lag. We have an ability to add custom reader endpoint for load balancing. This also comes very handy to get better performance if you have a specific application that has specific query patterns, then that influences the caching layer. Depending on the queries, the buffer pool, the caching layer adapts to that type of query. So if you have 2 different reader applications that has total different patterns, it's better to use multiple readers, and we have an ability to combine multiple readers under the reader endpoint so that you get better load balancing and scalability and better performance because you can control the buffer pool. Let's look at how you would configure a database cluster. In this example, I'm showing that in the lower half, there's a storage fleet that contains the data for the database. You have one writer that the OLTP application writes to, and there is a standby reader instance in availability zone 2 that will take over as the writer if the primary writer instance fails. And there is a reporting application that does a lot of reads. It is connected to a reader instance in the availability zone 3. The database configuration input is primarily driven by, the first one is the application architecture. Application architecture influences the size of the database instance to meet the read-write throughput and latency requirements. So in this case, the OLTP application would have certain characteristics of supporting a certain type of load. And based on that, the person who is configuring the database cluster can decide the size of the database instance. It could be 1 core or tens of cores, depending on what is needed. And the availability requirements are used to decide if the database instance needs to be in a single AZ configuration or a multi-AZ configuration. Aurora supports both. In case of single AZ configuration, there will be a single writer, and it can also be used for reads. In case the writer instance fails, a new instance has to come up. In this case, this is a multi-AZ configuration. You have a reader instance that is ready to take over as a writer functionality, and there is a reporting application that has its own dedicated reader instance. So now you might ask, what does the system give you? Aurora system takes care of storage and IO scaling, durability, backup restore for disaster recovery, and so forth. Essentially, the lower half of the database stack is taken care of. It's completely managed for you. You don't have to provision storage if you want to go till 128 terabytes in case of Aurora. You don't have to provision IO capacity. The storage is auto scaling, auto healing. You don't have to worry about the durability of the data. What happens if the database instance, the compute instance fails? We take care of that too. Our monitoring system is able to quickly identify whether a database instance, the compute node, is functional, and it fails over if the configuration is done such a way as in this example, or it would spin up a new instance as replacement. You can also configure Aurora cluster for read scalability, wherein the cluster can auto add the reader instance based on the load signals. So this is what takes in are the things that you need to do for configuring a database cluster. So the key part is database capacity management, and it all depends on the application configuration and requirements. So I show here 3 different types of workloads. The first one is the spiky workload. The second one is infrequent workload, like a dev test workload. And the third one is a periodic workload, like an e-commerce workload that has a specific pattern throughout the day, throughout the week, throughout the year. Right? If you provision the compute capacity, the database instance capacity for accommodating your peak workload, it can get expensive. It's obvious because most of the time, in case of the infrequent workload, the database instance is not being used to its fullest capacity that you have already provisioned. Right? So if you try to save cost by provisioning less than peak, you end up impacting the customer experience, and also you might have a business impact by not handling the peak workload. You might be throttled. So the middle ground is continuously monitor and manually scale up and down. This is hard because you need to have the expertise, and you also risk outages. If you had to do it on your own, you would have to go from one sized EC2 instance to a bigger size or a lower size, depending on whether you scale up or down. And that during that period of time, the database is not functional. So you risk outages. This is where serverless comes in, and I'm happy to introduce you Amazon Aurora Serverless V2 that is in preview. A serverless auto scaling configuration for Amazon Aurora that now supports even the most demanding applications and database workloads. This essentially means that you can run any type of workload, the type of workloads I showed, e-commerce, live production workload, a dev test workload, or a spiky workload. The first thing that we do is we scale instantly from hundreds to hundreds of thousands of transactions in the fraction of a second for the compute capability. So in this graph, you can see that as the workload ramped up quickly, the capacity is able to detect it, and we were able to add capacity. And we stay one step ahead to making sure that the database is not throttled. When the spike goes down, the system notices that the load is going down and it closely follows it in a more conservative way, but in a fast fashion so that you don't end up over provisioned. The scaling happens in a fine-grained increment to provide just the right amount of database capacity. If you were to do it on your own, the choices of the EC2 instances doubles in size. So if your application actually needs 5 cores and you are in 4 cores, you have to go to 8 cores, having 3 extra cores that you don't need. In this particular case, in Aurora Serverless V2, we can add just the right increments. You get the full breadth of Aurora capabilities, including multi-AZ, global database, backtrack, cloning, and all that functionality that you get in the provisioned Aurora. By doing this serverless V2, we expect 90% of cost saving when compared to provisioning for peak workload. This is because that the capacity of the system is added exactly at the time it is needed and it scales down quickly. So you don't have to provision for the peak and underutilize the provision capacity. Let's look at how we do read-write scaling. In this diagram, I'm showing that the storage fleet already has the database storage resident, but the compute capacity, the database instance, is not attached to the storage fleet, but it is resident. We have a new function called as router fleet, and we have an application. When the application tries to connect to the database, it actually connects to the router fleet. So in this case, it's a read-write connection. The router fleet takes that connection and it finds that the database capacity is not there. So it quickly spins up from 0 to as low as 0.5 Aurora capacity unit, ACU. One ACU has approximately 2 GB of memory with corresponding CPU and networking. So essentially the router fleet spun up the capacity using the monitoring fleet and the control plane that we have, and that database capacity is now able to attach the storage volume and it is ready to serve the queries. And the router fleet is connected to the database instance. Now application can send the queries and the router fleet would send it to the database capacity. As more load increases based on CPU and memory usage, required ACUs are instantly available to the database. In this particular case, the application opened another connection and it gave more queries. So the database capacity grew up in place, and we are able to do that by making the database engine and the virtualization to cooperate very well so that we can add more CPU and memory and networking instantly so that your existing connections are not dropped, your existing buffer pool is not affected, but the database engine is able to add more memory to the buffer pool so the caching is better, and we are able to add more threads, more cores so that your CPU is increased. So the database capacity just grows up in place. And the smallest increment of ACU addition is 0.5 ACU, and the maximum supported is 256 ACU. This is very different than scaling up by using a different instance. It's in-place scaling and it's instantaneous. Say the database workload vanishes, but the connections are still resident. What we do is, based on the configuration, the database capacity can be scaled down completely to 0, while the connection is still held active with the router and the storage is available for immediate reattach. And in the configuration, you can set to not to go to 0, because if you go to 0, the next time you reattach, the buffer pool has to be rehydrated and there is a performance impact there. So you can configure the system saying that hold a minimum capacity of X number of ACUs, and the database capacity will be held so that when the new requests come in, it can be served immediately. Let's look at how we do read-only capacity. Aurora database cluster in Serverless V2 can be configured with maximum read-only capacity of 15 times 256 ACUs. This mirrors the ability of the provisioned Aurora database cluster to have up to 15 reader instances. Each reader instance can serve up to 256 ACUs. Read-only database capacity is automatically added based on the load. In this particular case, the application already was using read-write connections and the writer was available, writer capacity was available. In this case, the read-only connections are opened and the reader capacity is added. And we are able to scale both vertically up to 256 ACUs, and we can add horizontally by adding more readers transparently behind the router fleet. And the application can just open new connections, add more workload. Let's look at mixed configuration. If you have a database instances in your existing provisioned Aurora cluster, you can make those instances to be part of Aurora Serverless v2 configuration via console or API. In this example, the database writer instance is in provisioned mode. That means that the customer has configured the writer instance with a particular instance type and size, and they're able to directly talk to the instance using the writer endpoint or the cluster endpoint. But this cluster can be configured with the read capacity, read-only capacity, to be managed by serverless v2, which means that you have the instantaneous scaling and also ability to go for 15 times 256 ACUs based on the load and based on the configuration. Let's look at a demo, and I request Chayan to give the demo of serverless v2.
All right, let's get started. Thank you, Murli. For this demo, I'm going to focus on the instant and fine-grained scaling characteristics of Aurora Serverless v2. And I'm going to use an online store to walk you through this demonstration. What you see here is a CloudWatch dashboard, and the blue line is showing the orders being processed by this online store. The orange line shows the database capacity. The orders are being represented on the left-hand side vertical axis. And the database capacity in Aurora Serverless is measured in Aurora capacity units, or ACUs. As of now, the database is running on 4 ACUs, and we are processing a baseline workload with about 10 orders per second. And the database capacity in ACUs is being shown on the right-hand side vertical axis. So these are the metrics we'll be watching on CloudWatch. I've already created a serverless v2 database for you. That's not what's exciting or interesting. It's a regular process for creating Aurora databases. But what we are going to see here is, as we increase the number of orders, the database adjusts capacity instantaneously in response to those orders. And that's what we'll dive deeper into. Now, I'm going to show you also some of the internal metrics from the database engine and what's going on within the engine as the scaling happens. So let's log into my database. I've done that already, and walk through some of the internal metrics. So what we see here first is max connections. So that tells us the number of connections being supported by the database with the current capacity. As we increase the number of orders, the database reacts to it, adds more capacity, and number of connections that it can support also increases. We also have current connections, which is, as it says, active connections to the database. We have purposefully selected a workload which is CPU intensive, and so we'll not see this number get anywhere close to the max connections. In MySQL databases, buffer pool size is a very important aspect. Buffer pool is the primary cache of the database, and it is responsible for storing your data pages and indexes. And what we are going to show you here with the demo is, as the number of orders go up, the database capacity gets adjusted. We also expand the buffer pool to support your workload with it. Another important aspect is the InnoDB history list length. So this represents the amount of changes going on in your database. InnoDB is an MVCC, or multi-version concurrency control storage engine for MySQL, which means that if there are multiple transactions modifying the same rows, it can provide a consistent snapshot of that row to the transactions individually. And it does so by maintaining multiple versions of that record in undo logs. Now, the challenge is that if this history length grows too long, then your DML throughput, the selects, updates, inserts, could slow down. And that's not ideal for database performance. So MySQL maintains or runs background threads called as purge threads, which come in and clear out these transactions. So as we look here, we see that we have run this query and the InnoDB history length is about 3412, and that number is not as important. What we would want to keep an eye on is the fact that this number keeps changing. It will go up and then come back down, indicating that the database is adjusting or purging the records. And the purpose why we are showing this metric to you is that Aurora Serverless not only optimizes resources for your foreground processes, for your queries and connections, but also for your background processes, such as purge, to make sure that you get an optimal performance out of your database. So now that we have seen both the internal metrics and also the CloudWatch metrics, I'm going to exit out and run a script which is going to continuously execute this query every 5 seconds. And that way we don't have to manually run this query. Next, I'm going to simulate a sale. So we are running a promotion on our products in the online store. And I'm using Artillery, an open source tool, to execute this. There's a Lambda function which is doing the processing of the orders. It's not a simple select. There's a bunch of inserts, lookup of the catalog, aggregations that are happening, updating the stock. So there's a lot of operations going on in the background with it. So with that, as Artillery has kicked off, what we'll expect to see is increasing number of orders. And that's what we are starting to see in the blue line. We see the orders surging. As of now, there's enough capacity so the database is able to accommodate that surge. What's great about Aurora Serverless is whether you have a modern application or you have a traditional application, irrespective of that, it helps you operate the database without having to worry about the capacity of the database. You no longer have to provision for peak and pay too much, or under provision and provide a poor experience to your customers. So let's the sale proceed a little bit more. As it proceeds, we'll speed up a little bit. We see that there are certain spikes, and the orange line, which is showing the database capacity, is also following it very closely. Let's zoom in a little bit and look what's going on. Again, the orange line is falling very closely. The database capacity is falling very closely in tandem, in lockstep with the orders. There's a little bit of variability that we expect to see in general in any case, because these are humans placing orders. That's what we are simulating. So that's why you see the fluctuations. And now we are reaching a point where we have reached a peak load. So we see that the database scaled up to support almost up to 1700 connections, 16 gigabytes of buffer pool size, and the buffer pool on the history, InnoDB history length has also increased. The sale's now ending, so we see a step down. So we are seeing a staircase form, and that is for a reason. It's purposeful. We don't want to scale down as quickly as we scaled up because we don't want to take away too much or a bit too much of your buffer pool and start impacting your workload. As the sale finishes, it goes down to the baseline workload, which was about 4 ACUs of capacity, 10 orders per second, as we saw initially. And let's hop back into the database. We also see that it has scaled down, 150 connections, and about the InnoDB history length is also going above 3,800 now. We'll quickly see, yes. So there, the purge kicked in and reduced the length. So we are seeing that even though the scale down is happening, Aurora Serverless is making sure that we don't take away capacity in a way that it starts impacting your background processes. So that's a wrap. That brings us to the end of our demo. What we saw is that Aurora Serverless is able to scale up instantly and in fine-grained increments, just in the right amounts, providing you the resources as your application needs. And in addition to providing you the right resources for your foreground processes, it is also balancing the background processes so that you get the best price performance for your database. Over to you, Murli.
Thank you, Chayan, for the demo. Let's do a quick recap. We're happy to introduce you Amazon Aurora Serverless v2. It's a serverless auto-scaling configuration for Amazon Aurora that now supports even the most demanding applications and database workloads. This means that you can put your production workload and not just your dev test workload. As Chayan showed you, the workload is able to scale instantaneously, and you can go from hundreds to hundreds of thousands of transactions in fraction of a second. We can scale in fine-grained increments, so we are not doubling the capacity every time we scale up, and similarly to scale down, we add exactly how much is required based on the workload that the database is incurring. We have the full breadth of Aurora capabilities, including multi-AZ, global database, backtrack, loading, and so forth. And you would save up to 90% depending on comparing to the provisioning for the peak workload. And the system takes care of scaling up and down to save the cost. I recommend related sessions on Aurora Postgres, Aurora Storage, and Global Database. Thank you. Please complete the session survey.